Recording is rolling. It is Wednesday, November 13th. So we're going to do these textbook puzzles today. Textbook puzzles. This is chapter 7 from your book. And just tell you what, whatever we do in class today, okay? Just whatever we do in class today is all the ones I'm going to pick up. If you miss something, then for the next couple days, but my turn today, it's right. All right. Huh? All right, so tomorrow, mechanical advantage lab. Guys, let me show you guys a little bit about pulleys and mechanical advantage, so you guys know what to look for tomorrow. You can think on this tonight. So I have a pulley system right here in front of me. Do you guys see it only takes a little bit of input force to lift this really heavy weight down there? Right. But do you guys see I'm pulling lots and lots of string and only moves up a little bit at a time? You see that too? All right, so what is this mechanical advantage? Mechanical advantage is there are a couple perspectives. It could be a ratio of distances moved. That's called ideal mechanical advantage. Or guys, everybody look here. Look up here. What's going on? Right. Or if you take the ratio of the forces, that's called actual mechanical advantage. Now, really, these two should be almost the same as each other, but maybe slightly different. Right? And come back to there. Come back to y. Okay. But the guiding principle is conservation of energy. Work input equals work output. So force times distance in could be equal to force times distance out. If you have 100% efficient. Okay.
Is this how a rock wall works? Like when you are attached with the harness and they no.
It could depending on how you break it up. Yeah. I have to see how it's rigged up because there could be lots of ways to do that. So I'm gonna have you guys rig up each one of these tomorrow, right? And they'll each be a different mechanical advantage. Yes, if you're climbing a rock wall and say if you hook it up like this, you're not really getting an advantage. The amount of force you pull with, I think it would be equal to your weight, right? But if you rig up, say like one of these other ones, then yeah, maybe you only need a small input force, and go up really fast, really easy. Okay. Right. So start with this one then. Right. So, yeah, suppose this weighed 300 newtons. Guess it weighs 300 newtons. Right. Here's what would be the tension in each one of these strings. This weighs 300 newtons. Is it split three ways? Yeah, 100 newtons. You guys see 100 newtons on each one of these, right? And then, oh, so how much force would you have to pull with on the side of the spring scale? 100 newtons, right? Right? Because if you could only pull with 100 newtons, you could still lift something that's 300 newtons of weight using this system. You could do that. You guys see that? Right? That's this actual mechanical advantage is what I was getting at, right? For the ratio of the forces, right? But you can see that in terms of distances also. Guys, suppose you lift this 10 centimeters. You guys ready for a new question? You lift this 10 centimeters. Guess how much string you had to pull on the side of the spring scale?
30.
So like 30 centimeters, right? This is 3 times as much. If this is 10 centimeters, this has to be 30 centimeters. It's still a 3-to-1 ratio, but the other way in terms of distances, right? That's called ideal mechanical advantage. You could just look at the system and say, well, it's going to be 3-to-1 just based on the geometry. So it's ideal, right? But if you try this out and you actually test the forces, no, wait, what I said before, if this was 100, sorry, if this was 300 newtons, or you only have to pull with 100 newtons, that might not be exactly true. Do you guys think there might be a little bit of friction forces here? Or maybe these strings aren't exactly vertical, so there's a little bit of trigonometry. Maybe it's more like, instead of 100 newtons, maybe it's like 105 or 110, maybe something like that, right? So this actual mechanical advantage might be a tiny bit less than 3-to-1. And then last part of this lab is to figure out the efficiency. That's this Greek letter eta. It looks like an N with an elongated tail on it. Right. So tomorrow you're gonna bring up each one of these. You're gonna say what's the input and output forces and distances. Therefore, what's ideal and actual mechanical advantage. Just playing off this. Okay. And then finally, efficiency. Now there's different ways to get efficiency. One way is just take the ratio of the what is AMA compared to IMA. You take the ratio. Okay. So yeah, that'll be tomorrow. Right. Right. So you guys good with lab tomorrow? What's going on? Right. So some more stuff. Friday, there's Justin's in the auditorium. So they're splitting you guys up like this. Period 1 is going to be juniors, last names A through L. Period 2 is juniors, last names M through Z. Period 3, seniors, last names A through L. Period 4, seniors, last names M through Z. Most of my students are like juniors or seniors. So I think I'll probably do a Kahoot on Friday. So you guys can learn some stuff if you're here. And then if you're not here, then probably be all right.
What is that for?
That's Jostin's. There's a Jostin's presentation. Justin's does a lot of stuff. I think they do graduation gowns and yearbooks and photos. That they do all that stuff, right? I don't know exactly what they're going to be talking about, but I'm going to guess that graduation gowns is probably somewhere in that presentation. Just help you guys get you guys ready to graduate, right? All right. All right. So, yeah, so we're doing these puzzles today. You guys can probably turn in these puzzles today because we're just whatever we're doing class is all we're going to do on those. I will get you guys your next in-class quiz sometime next couple of days. Right. So you'll have a few days to do that. All right. Next week, there's going to be this in-class quiz. Next in-class quiz next week. So I told you guys a few weeks ago I was going to get you guys 2 of those before the midterm. The first one's next week. So it's going to be mostly on forces and Newton's laws of motion. There's going to be a couple of projectile questions and a couple of energy questions. Right. So it's going to be all multiple choice. These questions are a little bit easier than the questions I tend to ask you guys, but well, we'll see what you guys have. If you fundamentally understand physics, I think you'll be all right. Allow you guys 1 paper of notes. So if you have a page of paper, whatever you want to write for notes, formulas, examples, you can bring that in and use that for notes, right? Okay, so any questions about any of this stuff? Yeah.
We have a review of like what's going on.
Yeah, I can do a review with guys. Yeah, we did. All right. All right, so let's solve some of these puzzles then. Got chapter 7, energy. All right, so looks like this first section here is just some warm-up puzzles. Let's pick a few off the right. How about plug and chug, work as force and resistance? Let's do how about number 31. Number 31. Right, you guys got the paper out? Right. Because if you're just following in class with me here, then right, you probably have these done by the end of class then. Number 31. This is chapter 7. Chapter 7, energy. You guys write your name on your paper. You guys write your name. Okay. Calculate the work done in lifting a 500 Newton barbell 2.2 meters above the floor. Okay. So barbell. This thing weighs, I'll say mg weight is 500 newtons. Okay. So, hey, do you guys think that F lift, the lifting force, would have to be how much? 500 newtons. Okay. You lift this whole thing. Distance equals 2.2 meters. Okay. Right. Guys, go ahead and solve that. Work is equal to, guys, tell me how much work was done. How much energy did it take to lift those barbells? Huh? 1,100? That's right. Yeah. So it's F dot D. Okay. So it's 500 newtons force lifting 2.2 meters. And it's straight up. So this dot product, well, they're all in the same direction. Cosine of 0 degrees of 1 as on 100%. Yeah. So it's all going to translate into the work. Okay, so that's 1,100 what? What's the unit for energy? Is it newtons, joules, or watts?
Wow. No, joules.
Joules. Yeah, joules. There you go. 1,100 joules. Okay. And whoever was lifting the barbell, you know, maybe that came from his muscles, could be, right? Like that. All right. Let's skip down to number 33 is also a barbell. Let's do 33 because it's a barbell also. Show that the power expended when a 500 Newton barbell lifted 2.2 meters in 1.4 seconds. Okay, so it's a continuation of the one we just did. Let's throw in a time. So it's number 31 in time of 1.4 seconds. So power. Guys, power is equal to whatever what? Oh, yeah, work over time. There you go. Okay. Yeah, you guys remember this one right here? Power is work over time. Okay. So it's you think of it like a rate transfer of energy, right? How fast is energy being transferred? So work over time. It's like 1,100 joules and 1.4 seconds. You just divide that up. That's 700 and 700 785.7. Can I round that to 786?
Yeah.
And 786 what? What's the unit? What's joules per second?
Watts.
Watts. Yeah, watts. Right. Power can be measured in watts, right? Right. It's like a rate transfer of energy. Right. In the premise, they actually gave you the answer. You guys catch that too? It says, show that it's 786 watts of power. Oh, we just did. There you go. That's the answer. You got it right there. All right. Let's do number 37. 37. 37. Kinetic energy of an 84 kilogram scooter. So mass equals 84 kilograms. Moving at 10 meters per second. Speed equals 10 meters per second. What's the kinetic energy? Guys, what's the formula for kinetic energy? One half. Yeah, how's that finish up? One half mv squared? You guys are kinetic energy? Guys, kinetic energy, that's energy of motion. So it has something to do with speed, which I'm calling V, right? Right. Also mass, right? So one half mv squared. And so let's take one half. I got a mass of 84 kilograms. Speed of 10 meters per second. I'm gonna square that. Put it all together. So there's the number on my calculator, but that number has unit attached. Guys, what's the unit for energy? Joules. Oh yeah, 1400 joules. Okay. So if this is on a scooter, if the scooter has a motor on it, then that's how much energy it drew, say like either out of a battery or out of a gallon of gasoline, right? Or if you're like pushing the scooter with your legs, like pushing on the ground, then maybe that energy came out of your muscles, or that energy came from somewhere, right? Right. What next? Let's do. Oh yeah.
Ones we go over in class too, or all of them do.
Just ones we do in class. Yeah, that's all. So what we did, we did 37. We did 33. We did 31. Yeah, I saw those circle ones ago. How about, well, let's do 38. 38. Says, show how much work was done when a 3 kilogram block of ice, so mass equals 3 kilograms, is moved to a speed of 4 meters per second. V equals 4 meters per second. Okay, so it sounds kind of like what we just did, isn't it? Okay. Guys, go ahead, solve that. What's the kinetic energy associated with that? 1/2 mv squared, right? That's 1/2 at 3 kilograms.
19.
Guys, what's 4 squared? 16. What's 16 divided by 2? 8 times 3 is 24. And what's the unit on that? 24 what? Joules. 24 joules. Okay. So if that mass is moving that fast, it has this much of energy in motion. So 24 joules of kinetic energy. Okay. Now, what the question actually asks is how much work was done. Actually, here's literally what it says. It says, show that 24 joules of work is done. Hey, look at that. That's what we just did. Well, if it has 24 joules, it had to get that from somewhere. Oh, it got that by the work that was done on it. So if you like push or pull on it, like that, right? So it's called work energy theorem. That's why it says it right here. It says work energy theorem. So the work you do on something can translate to its kinetic energy. If it's not being pushed up any hills, there's no energy loss. Okay. Let's see. It's good. Next one. Let's do the ones with the pictures on them on the front. So 48, 53, and 54. Yeah, we'll look at 119 when we eventually get there. And then Yeah, okay. Well, let's start with it. And so, see, numerical order, I guess the next one is actually number 48, right? 48, in a hydraulic machine shown. Ooh, you guys see this hydraulic lift here? That's gonna show up next semester. We'll talk about something called Pascal's principle. You guys see this picture again. You observe that when the small piston is pushed down 10 centimeters, the large piston is raised 1 centimeter. Like if there's some hydraulic fluid in here, maybe I'll just call it water. Do you guys think that the same volume of water being pushed out of the left is entering into the right?
Yes.
Yeah, right. But it's different areas, so it's going to be different height changes. Right. That's a different way to think about it. The small piston is pushed down with a force of 100 newtons. What is the most weight that the large piston can support? Right. Now, here, I'll write down something from next semester called Pascal's principle. Pascal's principle. Okay. Says that the pressure is the same on both sides. So pressure on the left equals pressure on the right. Right, so pressure on the left side is equal to pressure on the right side. Okay. Now, we did talk about pressure a little bit a few weeks ago. Because pressure from a few weeks ago is what over what? What do you guys know about pressure? Do you know units for pressure? Have you guys ever pumped up your bike tires?
Yeah.
What unit do you measure your bike tires to pump up?
Oh.
PSI? Right? Does that stand for pounds per square inch? Right? Guys, pounds is a type of what? Force. Yeah, so yeah, weight or force. Okay, so some kind of force. And square inches, square inch is some kind of what? Area. Right? Force over area. Right? All right, so left side, force right over area right. So it could be like that, right? You know what? You know what? Force. This actually, I'm solving this a different. Actually, I'm going to start from scratch. Here's why we're not actually going to do this way. Okay. Next year we could do it this way, but it'd be a little bit complicated. Let's stick to the principles in this chapter, which is work in equals workout. So you'll see this next semester. So it's worth your time seeing anyway. But I'm going to do this. Work in equals workout. So we'll do like a conservation of energy type approach. Okay, we're getting sort of a mechanical advantage from this piston system, kind of like you guys will tomorrow with your pulley system. Okay, so that's force in, distance in equals force out, distance out. Okay, yeah. So ignore Pascal's principle. That's a different way of solving it. We'll do next semester. Well, we're going to do work in equals work out. Okay. So. Right, because they told you on the left side, if you push down 10 centimeters, the right side can lift up 1 centimeter. Right, you see it's a 10-to-1 ratio in terms of distances. Right, how many of you guys think it's also going to be a 10-to-1 ratio in terms of forces, just the other way? Yeah, right, makes sense. Right, so I'm pushing with 100 newtons on my end, so like that, right? And we're solving for F out. I bet F out is going to be like 10 times. Right? Oh yeah, actually that is exactly right because the centimeters cancels. So the output force, like the greatest weight you could lift, it's right there. 100 times 10 is 1,000. Right? And then the unit left over is newtons. There you go. Right. So the fact that the ratio of the distances moved is 10-to-1. The ratio of forces is also 10-to-1, just the other way. So now you can lift something 10 times as heavy. That's like getting a mechanical advantage of 10-to-1. That's a mechanical advantage. Okay. Of 10-to-1. All right, guys good? All right, ready for next one. Next one. Number 53. Roller coaster ride starts from rest at point A. I think we looked at a few roller coasters, right? Rank the quantities from greatest to least at each point. Speed, kinetic energy, and potential energy. So 53. Here, I'm gonna kind of redraw their picture here. We got roller coaster is doing something about like this. Good. Close point A, B, C, D, E. Okay. So speed, okay, from greatest to least. Guys, which point is going to be the greatest speed? Where's it moving the fastest?
D. E. D.
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 D
Yeah.
because it's going-
How do you know it was point D?
Because it went down something, so it's go faster.
Yeah, because it's the lowest point, right? Do you guys remember? Here's the last lab that you guys did. If you're trying to solve for what's the maximum speed of the pendulum, you know that would be at the lowest point, right? Right? Like if it went up and then it came down, if it went even lower somehow, then whatever's the lowest point. Because at the lowest point, it has the smallest potential energy. Right? In fact, I could define gravitational potential energy as 0 at point D, 0 potential energy, and it would be all kinetic energy, wouldn't it? If it's all kinetic energy, it would also be the greatest speed. Right? So I think the speed at point D would be the greatest. Guess what would be the next fastest speed?
B.
B. What's the next fastest speed?
C.
Yeah, C. And then
E.
E.
A.
Yeah, and then yeah, speed at A, which is equal to 0, by the way, because it starts from rest. Right there. The speed. Question B was kinetic energy. So, guys, is the kinetic energy going to be exactly the same ranking as the speeds? Yeah, because the mass is the same everywhere. So wherever's going the fastest has the greatest kinetic energy, and so on. Right? So kinetic energy, I think, is going to max out at point D, followed by B, followed by C, followed by E. Whoops. Right, followed by point A, and at point A, it's equal to 0. That looks, we should say 0 joules, right? Because we're talking about energy. 0 joules.
So
at point
would
A.
C be A would be first?
So at point A,
A.
where it's the maximum height, it has 0 speed. It also has 0 kinetic energy. Yes.
No, for potential energy.
Oh, for potential energy. Okay, so that's the next question. Let's go. And so potential energy, potential energy. So guys, where's the greatest potential energy?
A.
Yeah, point A. So I'm going to use capital U for potential energy. So subscript A, that would be the most. And what's the second most?
E.
E, and then
C.
C, and then
E.
B.
D.
Yeah, and then D. Okay. In
What was
fact,
the unit for H for the 0 in the middle that you want?
oh, that's a J. That's joules.
Oh, that's true.
J for joules. Okay. Now, if at point D, if you define that as like the ground level, like the lowest point it's allowed to go, that would be 0 joules of potential energy there too, wouldn't it? Okay. So remember, kinetic energy, the formula is 1/2 mv squared. The faster it's going, the more kinetic energy. Potential energy is mgh. So the higher it's located, the more potential energy. Very good. Right. So I think if I'm thinking about this is an animation. It starts off at rest point A, give it a tiny push. Right. It speeds up really fast towards B, then it slows down up towards C, then speeds up again towards D. It's going as fast as it's ever going to go at D, and it slows down, getting up to point E. And it's still moving at point E, just not as fast. All right. 54. Rank the scale readings from highest to lowest. The scale reading. Hey, look at that. That's your mechanical advantages right there. Right. So let's think in terms of numerical values. Like, guys, what if this weight is 100 newtons? Okay, 100 Newton weight. What is the scale reading on figure A? If it weighs 100 newtons, do you think all 100 newtons show up on the spring scale?
Mhm.
Yeah, yeah. And I think that should be the most because I think he's getting a mechanical advantage from the other ones. So 54. Yeah. I think the force on A is the most. That's more than something is more than something. So force A is the most. Because that's 100. It could be 100 newtons.
C would be the next one.
Yeah, C is the next one. Because guys, if that block again weighs 100 newtons, what's the spring scale rating this time in C? 50. Yeah. Yeah, see, this 100 newtons, it's split like two ways. It's like being pulled up by two ropes. So that's going to be the next one for C. Okay. Now, oh, wait, did I lie to you guys? I sort of did.
What?
Guys, what is the force in B? Force rating in B.
30?
Here, guys, this is 100 newtons, right? 100 newtons.
It'd be 33, right?
You guys see two ropes being pulled up here?
There's 3.
Well, there's only two attached to this movable pulley.
Yeah.
So it splits two ways. So it's like 50 newtons. The same as it is in C. Actually, B and C are the same. So just say equals. Okay,
Why is it-
rewrite that.
Why is
So,
it C 100?
Force A is the most.
Mhm.
Then force B and force C are the same. That's actually what it is. B and C are the same, and A is the most. Okay. 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 So because both B and C, those are both 2-to-1 mechanical advantage. Actually, I think I have a poster on this too. Here, well, here's a little bit bigger. Right. So here's the 2-to-1 I can have you guys build tomorrow. The rule of thumb is if you look at the movable pulley, you guys see I have two pulleys here. One of them is fixed and one of them is movable. You guys see this one on the ceiling is like fixed to the ceiling. It's not moving at all. Okay? But this one down here is free to move up and down. Okay? I have one in class too. You guys can see that too. If I move this up and down, you guys see these top two pulleys are fixed in place, but this bottom pulley is like moving up and down. So if you hone in on the movable pulley and say, okay, there's one weight pulling down and there's two strings pulling up, that's a giveaway that's going to be a 2-to-1 mechanical advantage. Okay, 2-to-1. Right. Right. And that's true for both of these pictures, B and C. They're both a 2-to-1 mechanical advantage. Okay. Right. Right. Number 119. Consider a satellite in circular orbit above. Oh, yeah. 54. Yeah. Okay. So A is the most force because it's a 1-to-1 mechanical advantage. 1-to-1. Right. There basically is no mechanical advantage on force A. Right? If this thing weighs 100 pounds, he has to pull with 100 pounds to lift it up. Right? If there's any advantage, he gets to change the direction of the force, but it doesn't become stronger. Right? B and C are the same mechanical advantage. Both of these, he's getting a 2-to-1 mechanical advantage. He's amplified his strength by a factor of 2. Okay. Right. 119. Got a satellite in circular orbit above Earth's surface. In chapter 10, we will learn, I think we did this already. We will learn that the force of gravity changes only the direction of motion of the satellite in circular orbit, not the satellite's speed, right? Because if you go way back in this class to like September, if there was a force, we talked about acceleration as in a linear acceleration, so it would speed something up or slow something down, right? But then more recently, you guys learned about centripetal force, and that's this gravitational force is acting as that. Work done on the satellite by the gravitational force is 0. What is your explanation? So I'll write it out with you guys here. Here's 119. Here could be the Earth, E for Earth. Here could be a satellite. Right? Satellite's going around in a circular orbit, right? Circular orbit. Now, if you do a free body diagram, here's the force. Call it F sub G, gravitational force. But the motion of the satellite is always perpendicular to that. Isn't that true? So the force on the satellite, which is directly towards Earth, and the direction of motion of the satellite, tangent to that dashed line path, those are always perpendicular. Right? So I could say the gravitational force is perpendicular to the direction of motion. Right. And therefore, F dot D is always equal to 0. Hence no work. Right. That's a real short way to encapsulate that. There you go. Okay. Because you guys remember here, while you guys are writing that down, just a reminder, when I say F dot D, that's the same thing as the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. But cosine of 90 degrees is equal to 0. Therefore, no work. Okay. That's also true whenever you have a block sliding on a track or a roller coaster on a track. The normal force from the track, I mean, there is a force there, but it never actually does any work on the block or on the roller coaster because the exact same reason. The normal force and the motion of the coaster are always perpendicular, so there's no work being done. That was a poster too. Okay, are you guys good with that? So if you want a force to do some work on something, there has to be some component of that force that's in the direction of motion. Okay? And for a circular orbit, that is not the case. All right, so you guys get on the front there, go on the front. All right, so come on the back. Ooh. All right. Here's Paul Hewitt with his bowling ball here. Yeah, let's maybe hit these ones with the pictures again. All right. Let's kind of stand out. Boom, boom. Let's just do these 5 right here. We'll do these 5 and those will be the last 5. Right. So number 69, physics instructor demonstrates energy conservation by releasing a heavy pendulum bob, as shown in the sketch, and allowing it to swing to and fro. What would happen if, in his exuberance, he gave the bob a slight shove? Right, explain. Do you guys remember that video? So as long as he released it from rest, it only came up to the same height and he was okay. But if you gave it a push, remember he had to move his head, otherwise it would smash his face in? Yeah. Remember that? 69. 69. Okay. So, all right. If I can do this with a picture too. Okay. So starts here. So could have some potential energy plus the work from pushing it. Okay. Here it's all kinetic energy. Here it's potential energy plus the additional energy that it took to lift to that height. And when it swings back, it's going to rise up to that same height just on the other side. Okay. So if you push the ball, then it has energy in addition to the initial potential energy. So it will rise higher than it started. There you go. Remember, if you release it from rest, then it'll speed up on the way down and slow down on the way up, but it only ever goes to the same height that it started. Okay. But if you give it a push, now you've put in some additional energy, you've done some work. So it's going to rise higher than it started. Okay, that makes sense. All right. Number 100. Consider the identical balls released from rest on the tracks A and B as shown. When they reach the right ends of the tracks, which will have a greater speed. Right. Why is this question similar to one or from 4? Okay. there's one question there, but want to look at kind of two questions. Okay. So we got track A goes like this, and track B looks the same except it's got this dip in the middle. So here's track A and here's track B. I'll call this speed A. I'll call this speed B. You guys see speed A and speed B? Those balls? Okay. Hey guys, how does speed A compare to speed B? Is one greater or are they the same? What do you guys think?
A is less than B.
Yeah, I'm gonna go with the same. Because if they fell the same height, like if they both started say, like up here, okay. If you look at this height change, H, as long as it's the same height change, then they started off with the same gravitational potential energy, so they end up with the same kinetic energy. I'm gonna say these speeds are the same at the end. Okay. Right, guys, that. Okay. Now, what about a different question? What if I put like an end gate here? You guys see there's like a little finish line. And I want to know who takes more time to reach the end. I'll call it TA compared to TB. Okay. Guys, whoever gets the shorter time wins the race. Isn't that true? If it takes you less time, you win the race. Okay. Guys, who wins the race?
B.
Probably B. Yeah, probably B. I'm going to say it's probably more time for A than B. Okay. Okay. Now, it really depends on the exact geometry. I mean, if this goes down like the Mariana Trench deep, then I guess A would win, right? But if it's just a small dip, yeah, then ball B is going to speed up and it's going to go on this part of the track even faster. It's going to slow down a little bit, come up the hill. So that, yeah, they finish through this finish line with the same speed, right? But ball B is probably going to get there faster. Okay. Because it zips through this valley really fast. 102. Suppose an object is set sliding with a speed less than escape velocity. Okay, so maybe this is like the curvature of a planet, and then we got this like super straight track. It's actually level, not level with the planet surface, but actually level like in a cosmic sense, right? Describe its motion. Will it slide forever? Well, in this class, we've been saying if you have a level track that kind of curves around with the Earth, it could like slide all the way around the Earth if there's no friction. Okay. But if this is actually straight track, then is it kind of like it's gaining height from the planet, like it's sort of going uphill, sort of, right? From a planet's point of view. And if that's happening, then what's happening to its speed? So here's the planet. Here's your track. Here's your block. It's sliding. Okay. V. Okay. I think the block slows down as it moves away from the planet. And one way to explain why is that because kinetic energy changes into potential energy. All right, so that could take care of that one. Okay. Yeah, so if I say like you're going in a straight line on a planet, well, sometimes this implies you're actually going around the curvature of the planet, right? But going long enough distance. Yeah, but something crazy like that, ooh, yeah. You would be like sort of changing your height as you're going along. You've got some buildings here. These buildings are getting taller and taller. Kind of like you're going uphill. Right. Hey, you guys got on 102? All right. 112. In the pulley system shown, block A has a mass of 10 kilograms, suspended precariously at rest. Assume the pulleys and string are massless. There's no friction. No friction means that the tension in one part of the string is the same as any other part because it's the same tension throughout that entire string. Okay. Well, okay, they gave away the answer here. The other block would have to be 20 kilograms. Guys, this could be all hanging just what when they say precariously, it means like it's barely at rest. Okay. Okay, let's just redraw this to start with. So 112. Okay, we got a ceiling. We got a couple of pulleys. Now, this pulley on the left is fixed. This pulley on the right could be movable. It's allowed to move up and down, although it isn't because everything's at rest. Okay. Okay, and we got the string that goes like that, attached to the ceiling. Okay. This block A could be 10 kilograms. And this block B, okay, they gave away the answer right at the end. They said it does have to be 20 kilograms. That's true. Okay. Let's explain it in terms of the tension. There could be probably different ways to explain it. Okay, guys, what is the tension in the string everywhere? Tension in the string is what? How many newtons? 100 newtons. Okay. So
How'd you get 100?
that because guys, what's the weight of this block? Mg equals what? 10 kilograms times 10 meters per second squared. That's 100 newtons. Okay, this one is 200 newtons. This tension up is 100 newtons. This tension up is 100 newtons. This tension up is 100 newtons. Okay. Okay, so the tension string is 100 newtons, so that each block is in equilibrium. There you go. Okay. Okay. So 10 kilograms weighs 100 newtons, 20 kilograms weighs 200 newtons, and the tension in the string is 100 newtons. It only acts once on the left block, but the tension effectively pulls up twice on the right block. 100 plus 100 is 200 up, balance the 200 down. All right, makes sense. All good. So the string tension has to be 100 newtons. In fact, if you get a lot extra time tomorrow, I bet you could rig up exactly that. You could rig up that geometry. You could put a like 100 grams here and 200 grams here. I bet it would just fairly precariously be in balance. Yeah, you can try that tomorrow if you want to. Okay, last one, number 120. Consider the swinging balls apparatus. Hey, that's I got it right here. It's this right here, isn't it? And so let's take a look. Ooh, look at there. There's something like that. What do they ask about this? If two balls are lifted and released, momentum is conserved as two balls pop out the other side. We haven't talked about momentum yet. We're doing every book is written a little bit different order, so that's why they're talking about momentum. Okay. But momentum would also be conserved if one ball popped out with twice the speed. Here's what they're saying. So hang on. If you pick up two ball, momentum is just mass times velocity. Because this right here, what you're seeing is two different principles. It's conservation of momentum, but it's also conservation of energy. Right. Now they're saying if you just think about it in momentum terms, why isn't it that you drop two balls? You drop two balls. What if one came something like this, do a slow-mo? Whoa, wow, what if one came out with like twice the speed, came up like that? Okay. That would still show conservation of momentum, like that would be okay. But that wouldn't hold true for conservation of energy. Your energy would be all out of whack. Okay. So that would not show that. Discuss why this never happens. Okay, so here I'll just say 120. Sometimes you see that called Newton's cradle. So Newton's cradle. So it's weird. Down to like the last minute here. I'm just going to say this. Newton's cradle demonstrates both conservation of momentum and conservation of energy. And in terms of conservation of energy, think 1/2 mv squared. So if you have like two balls coming in at some speed, right? If you were to see like one ball leave with like twice the speed, it would have 4 times the energy. That'd be too much energy. So energy coming out of nothing. So we just try that, right? Right. If you write something like that, that'll be good enough on that one. Right. So Yeah, guys, if you wrote everything that I wrote in class, make sure your name's on it. Guys, your name on your paper. You can staple that together. Got a stapler up there. Throw that in the grade tray. I'll give you guys points for the textbook puzzles. Okay. And then tomorrow, of course, we're going to be doing this mechanical advantage lab right here. All right. Okay, and if you missed some of those in class, then just turn in the puzzles by the end of the week if you need to. And it's a wrap on today.